have the worst possible talking slot, is that half of you have already eaten, so you're about to fall asleep, and half of you are hungry, and I'm standing between you and lunch. So I'm going to try to make this entertaining. I'll start by saying the only Russian words I know are inappropriate in this venue. I did my undergraduate at Carnegie Mellon. My sophomore roommate was fluent in both English and Russian, and the only words I know are the ones that he used to yell at his mom on the phone. So they're probably not appropriate for this audience. Thank you all for coming. Today I'm here to talk to you about microservices and how we can secure microservices, particularly in distributed systems, but these concepts apply even if you're a huge monolithic Java application. So the concepts kind of apply largely, but I'm going to be talking about them in context with microservices. So my name is Seth. I'm a developer advocate at Google. Prior to that, I worked at HashiCorp. Prior to that, I worked at Chef. Prior to that, I worked at Custom Inc. and a few Pittsburgh-based startups. I did not work at Amazon, which is apparently one of the trivia questions. But I'm here today to talk about security kind of as a global concept. When we think about security, this is how traditional application developers think about security. You put a padlock around the keyboard and it's now secure. No one can touch that keyboard because there's a padlock around it, right? And this seems silly, but this is actually how many security teams and how many organizations think about security. We're going to put a padlock on the outside, and if you're inside the padlock, everything is secure, and if you're outside the padlock, everything is insecure. And sometimes we call those padlocks firewalls. So instead of kind of thinking about it this way, let's think about it this way. In a traditional application, our padlock is some kind of corporate firewall. So I have a load balancer. It might be a hardware-based load balancer. It might be a software-based load balancer. And then I have my firewall. That firewall is managed by the security team. If I want to open ports or allow traffic or change any of the rules, I have to contact the security team. The security team has to approve those changes, and they make those in the firewall. Inside the firewall, we have our trusted zone, or our secure zone. And this is where our monolithic application lives, along with our data store. Note that there's no microservices here. Our payment processing, our front end, our back end, all of that is in the application. So there's no mutual TLS. There's no inter-process communication. Our application does everything. Similarly, our database is self-contained. We're not sharding across multiple regions. We're not doing just-in-time content delivery or just-in-time data delivery. This is the traditional security model. If you have a monolithic application with a predictable data store, you can wrap the whole thing in a firewall, and it can be considered secure. You can have your security team manage those rules. Good to go. The challenge becomes, in a microservices architecture, things look a little bit more complex. Instead of having this monolithic service, we have microservices. And recall that the reason that we adopt microservices is to move faster. We can have individual teams working on small projects, delivering code independently of other teams. But once we introduce those microservices, a few things change. And instead of having one secure zone, we now have multiple networks. Those networks not only need to communicate to one another, but the applications inside those networks need to talk to one another. So my payment processing service needs to talk to my front-end service, which also needs to communicate with my search engine service. And these all require mutual TLS, inter-process communication. Additionally, when we mix in this concept of cloud, or just infrastructure and platform as a service, things get even more complex. So instead of a load balancer being a hardware device that is racked in my data center that my team controls, and instead of the firewall being a physical thing that the security team manages, these become constructs at the software layer. So things like the Google Global Load Balancer or the Amazon ALB or ELB, right? These are software constructs. Under the hood, they eventually hit some hardware somewhere, but that's not your hardware, right? That's someone else's hardware. It's a load balancer as a service. The same is true for the firewall. Whereas formerly we might be using something like, a Barracuda appliance that was installed in our data center, now we're trusting a firewall as a service. We're submitting rules, and we expect the firewall to process those rules. Things get even more complex when we start thinking about data, though. Many cloud providers and third-party companies offer managed services just for data. Things like managed Redis, things like managed Postgres or managed MySQL, right? These are offerings that are provided to us so that we don't have to, be a database administrator or optimize all of our tables and queries. The challenge is that now we have to find a way to access those securely. We might be accessing them over a public internet or an untrusted connection. So now we have to start thinking about things like VPNs and mutual TLS. But the absolute worst part of this architecture is the people. So the app team manages the network over there and the network over there, but the interns manage this network over here. And the security team manages the firewall rules, but individual teams might be able to manage them. And then there's this person named Chris, who just does all of the managed service stuff. Like, everyone has Chris, right? It's like the Brent of the Phoenix project. And when the managed services go down and Chris is on vacation, well, sucks to suck. So this is the reality of the direction that many organizations are moving. They're adopting microservices. They're splitting applications out into many subcomponents, and they're leveraging managed services, whether those are from a cloud provider or whether they're an individual service. So the challenge is we have to stop thinking about security like this. We have to stop thinking about security in the monolithic sense, where we can just put a padlock on it and say it's secure. That doesn't work anymore. I would argue that it never worked in the first place, but it was enough when we had a monolithic application. If you put a lock on a locker, the moment that that lock is unlocked, everything in the locker is accessible. All the papers, all the files, all the computers, they're all accessible. I have no control over who can access the computer versus who can access the files versus who can access the lunchbox, right? There's no controls. It is a Boolean open or closed. In order to think about what the future of security looks like, we actually have to look at the past. So this is a picture that I found of a very old Mayan castle thing. And I think it's from like the 1600s or the 1700s. It's obviously since been abandoned. But this thing from the 1600s does a far better job of security than most of your applications do. There's a moat, right? So you have to cross a moat. And then even once you cross the moat, there are multiple staircases. There are intentional dead ends. There are optimizations to make sure that the people fighting on the right-hand side, left-handed people versus right-handed people. It's an onion-like approach. You often hear this phrase in security called defense in depth, which means don't just think about security as a Boolean operation. It is secure or it is not secure. Instead, security is a scale, where the more secure something is or the less secure something it is dictated by all of the components that it depends on, and all of the components that depend on it. For example, if you run on a cloud provider, and your cloud provider is 50% secure, your application will never be more than 50% secure. It's not possible, because the underlying infrastructure which you're depending has a 50% chance of being insecure. Now, when you start compounding all these microservices, you can do an actual risk analysis, and you can quantify with real numbers the percentage or probability that an application is insecure. So let's talk about cloud, since I said that cloud is one of the things that's driving this kind of complexity. Cloud security actually helps here. So most cloud providers offer a dedicated team of people who think about security all the time. So my favorite quote that has been attributed to like 1,000 people everywhere is that if security is someone else's part-time job, are you as good as someone who's doing it full-time? So like at Google, we have a dedicated team of researchers who are constantly trying to break Google and Google Cloud for you. Application level security is one thing, but when you start looking at things like Spectre, right, CPU level vulnerabilities, these are things that as an application developer or even a security engineer, they're often outside of what I think about. Like I don't I don't think about security at the CPU layer. I kind of just trust that the CPU is going to work. So having dedicated security researchers who constantly think about these vulnerabilities and find ways to subjugate our very understanding of security help improve your bottom line. Cloud providers also have really cool physical security. If you've ever watched like a James Bond or like a spy movie, most data centers for cloud providers are actually like that. They have cool things like lasers that move around, and if you trip a laser, then the alarm goes off. Things like custom ID badges that are all manufactured in-house for supply chain, activity records, biometric scanners, iris scanners, right? Like everything that you've seen in the movies, those actually happen in data centers, especially data centers of like Google and Amazon and Azure, where regulation requires it. There's also hardware level security, right? So I talked a little bit about the CPU, but when you get a machine, right, when you get a laptop, like a MacBook or a Lenovo laptop, how can you actually trust that the hardware that is in that machine has not been tampered with? The shipping company could have opened it up and injected some malware. The manufacturer themselves could have injected some malware. How do you protect against that? Is that a threat that you're even thinking about when you deploy your applications? Probably not. And that's because cloud providers offer things like trusted boot. At Google, we have our own trusted boot modules that verify system integrity at boot so that if anything has been tampered with, it can't even boot. And then if you went to Liz's talk this morning, she talked a little bit about automated vulnerability scanning. This is something that many cloud providers offer as a service. There are also paid services and open source tools that'll do this for you. But at the application layer, especially if you're working in a language that has a large dependency ecosystem, things like Python, Node.js, Ruby, even Go to a certain extent, where you're depending on dependencies of dependencies of dependencies, you have to depend on some kind of automated vulnerability scanning to manage that dependency tree. Otherwise, a critical downstream vulnerability could affect your application, and it's unlikely that you're auditing every single dependency, especially with transitive dependencies down the stream. So I hope I've scared you sufficiently. Given all of this, like, what does modern quote-unquote security look like? So we have all of our microservices. We have this inter-process communication. We have some things that we manage and some things that we're delegating to a third party. The first thing is really straightforward. Encrypt everything. And I say that, and then I'll say don't encrypt everything with a little star and a footnote, which I'll talk about in a second. All data should be encrypted at rest. At the hard drive layer or at the storage layer, all data should be encrypted. However, when we're looking at data that lives in, say, like a database, it might not make sense to encrypt all of that data, especially if the underlying hardware is encrypted or the underlying hard drive is encrypted. I always like to give this example of email addresses. So let's take a quick poll of the room. How many people think that email addresses should be encrypted if they're put in like a database? Okay. Right? How many people don't? Cool. How many people didn't vote? Awesome. For those of you that didn't vote, you're right. Because the answer is it depends. If I'm a email providing company like MailChimp, where my business is to deliver email, there's probably a really good incentive for me to encrypt my emails. Because if an attacker gets those emails, my business is done. No one would trust me ever again. But if I run the world's largest online cat meme website, and someone gets all my email addresses, it's probably not a big deal, right? Like, people are not going to stop coming to see my memes just because I leaked some email addresses, especially since I'm not touting my security. On the flip side, though, when we encrypt things in a database, we lose the ability to do certain operations. If I am an email providing company where I do email as a service, and I'm trying to sell a big enterprise contract to someone, wouldn't it be great if I could go to them and say, hey, we have 16 million at google.com addresses in our database. Well, with SQL, I can just do that with a simple like select count star where email like percent star at google.com, right? But not if I encrypt them. Now I have to do an O of N operation where I go through each record, decrypt it, see if it matches a string, and then aggregate those results. So I took something that was like a very quick maybe 100 millisecond query, and now it might take hours to execute because I have to decrypt each row of data, I have to deal with the integrity issues of that data, etc. So encrypt everything where it makes sense. When things are at rest, they should be encrypted. When things are in transit or things are in memory or in use, you should have a conscious conversation with you and your teammates and your security teams about the trade-offs of encrypting versus decrypting the data. And this is where a threat model is very important. You have to come up with a threat model. It's impossible to be 100% secure. Just like it's impossible for your service to be 100% reliable. There are things outside of your software control plane that you can't control. Unless you are writing the programming language and manufacturing the hardware and writing every line of code and every dependency, you don't have full control over your system. And that's okay. You probably shouldn't. It's not a good use of your time. But you have to build a threat model. Given that you have a system that can never be 100% secure because you have downstream dependencies, we need to stop thinking about security as a checkbox, as a thing that I am either secure or I'm not. And instead, it's a scale. And instead of thinking about security as being this thing that we do in the front, we can think about security as a thing we do in the back instead. There becomes a point where it's no longer feasible to invest additional resources in protecting the system. And instead, we should invest resources in responding to an intrusion. And this is where things like dynamic, time-based, and revocable credentials are incredibly important. So let me ask a hypothetical question. How many people here work at a company that has an application that needs to talk to a data store? The rest of you, why are you here? It's okay, I know, you don't like to raise your hands. So for those of you that raise your hand, how do you get your application, the username and the password to talk to the database? If you work at a startup, you likely Google search how to create Postgres user. You click on the first Stack Overflow link, and then you copy and paste some code into an SSH session into a production machine. And then you copy and paste that username into a YAML file, and you check it into source control. That's a very real scenario that a lot of companies follow. If you work at a larger company like a bank or an enterprise, the process is very, very different. You file this thing called a JIRA ticket. The DBAs then Google how to create a Postgres user, and then they go to Stack Overflow. But they don't commit it to source, they email it to you, and then you commit it to source. So it's a very different process. The challenge is, one, every instance of your application now shares the same database credential. Okay, maybe that's not a big deal. Two, multiple humans have seen that database credential. Okay, maybe that's not a big deal. Three, if you revoke that database credential, you take down all of your applications. And four, you have no plan for rotation. It's very common to create that database credential, you put it in the YAML file, you check it into source control, or you put it in an environment variable somewhere, and then 12 months, 2 years later, it's still the same username and password. Well beyond like a brute force attack could find that password. Going back to the multiple humans thing though, let's say you are a very security conscious organization and you have some anomaly detection where you're looking at your database logs and, oh, it looks like this user is making queries that it shouldn't be able to use. How do you decide what caused that vulnerability? Was it Joe who created the credential? And now Joe is going rogue because he's mad at his manager and Joe just decides to like, screw this place, I'm out? Was it Chris who got the credential from Joe to put it in the GitHub repository because maybe Chris doesn't like her manager and now she's mad at the company? Or is it the application itself, right? Is an attacker actually connected to our machine and using those credentials against us? You don't know. And the reason you don't know is because you don't have provenance. Provenance is a one-to-one mapping between a credential and the entity that's using it, the human, machine, or process that is using that credential. When you have provenance, you can guarantee that this credential is used by this machine and only this machine, or this human and only this human. And that lets you very quickly make decisions like, can I revoke it? Can I rotate it? Who is responsible? Going back to the first point, that every instance of your front-end application is sharing the same credential. That means if you delete that credential, you take down your front-end application. You instead now have to coordinate some rolling deploy of all of your services just to rotate the database credential. If each instance of your front-end application had a different database credential, you could revoke one of them. It would automatically be removed from the load balancer or whatever service discovery type tool you're using, and you could rotate just that one out. And this is where we have to stop thinking about security, again, as a thing you do in the front versus a thing that you do in the back. Right? There's this famous T-Mobile thread from T-Mobile Australia where these people were exchanging on Twitter, and the support representatives could see the first 4 characters of your password on T-Mobile Australia. And this was a way to verify your identity. And some security-conscious Twitter user was like, hey, that's a bad idea because that means you're storing passwords in plain text. And the T-Mobile support representative who was working on Twitter came back with something like, what if our security is so super good that we never get hacked? And that's just fundamentally the wrong way to think about security. We have to assume that we're going to be breached at some point. At some point, an attacker is going to make it onto our network. Or, more likely, an existing employee with privileged access is going to be tricked, socially engineered, or encouraged to perform some type of malicious act. If you look at the large security vulnerabilities of the past 10 years, over 70% of them have been a result of social engineering or rogue employees, not some application level code things. Right? We look at things like Equifax, like, yeah, that was a really terrible application level bug that could have been patched. But then you look at other large data breaches, and they all come from an employee who had too much access, an employee who was tricked to give up their credentials or their one-time OTP codes, multi-factor authentication codes, etc. So we have to be able to respond to those incidents. The last thing, and probably the most important thing, is like this stuff is hard. I have a background in security because I'm a security practitioner, and I've been doing it for about 8 years now. I went to school for computer science, but I don't have like a PhD in cryptography. And when you start getting to like super low levels where you want to talk about like cipher suites and like ECDSHA curves versus RSA curves, like over my head, right? I have this firm belief that there are really smart people in the world who think about security all the time. And those people should scale. And the easiest way to scale their knowledge is to codify or capture as code their best practices, right? So who off the top of their head can name all of the deprecated TLS/SSL suites? We know SSL1 is deprecated. Is SSL v2 deprecated? What about v3? Should we use TLS 1.1? What about 1.2? We know 1.2 is good, but 1.3 is out right now. Can you use 1.3? Only if your users are using Chrome, right? These are things that you shouldn't have to know. Right? And I only know this because I looked it up right before this talk. However, there are people out there whose full-time job it is to think about these challenges. And then they can put them in an API, and we can just consume them. And if we trust them, and we trust that they're doing what's best, we can capture those things as an API, and you don't need a PhD in crypto. So I have a t-shirt, which I normally wear, but it was dirty, and I was lazy and didn't do laundry before I flew to Russia, that says, I don't have a PhD in crypto, and then the back of it says, and I shouldn't have to. And that's fundamentally my belief and kind of the core principle of the rest of this talk, which is that we've been kind of conditioned as an industry to believe that security has to be hard. But if we capture security and security best practices through a unified API, we can make security easy. And that's where tools like Vault come in. So Vault is an open source tool from HashiCorp. How many people have heard of Vault before? How many people are running Vault in production? I skipped like right there. Right? How many people are running Vault in like staging, QA, dev, test, your local laptop? Cool. So that's it. I'm done talking. For those of you that have ever seen me give a talk before, I'm not a big slides person. So we're going to go into the live demo part now. Who's excited? We have some good juju because Liz did a live demo earlier in this exact room, and it worked just fine until her laptop died. All right, can everyone see this? Hi. All right, so what is this Vault thing? So Vault is an open source tool that runs in a client-server architecture whose goal is to be this kind of central source for all secrets. I think the easiest way to explain Vault is to just show you, because it's so many things. So what I'm going to do here is I'm going to start a Vault server. I'm going to start it in dev mode. And I'm going to say that we'll run this thing. So just like that, I have a Vault server. It's now running. That wasn't very exciting. So we'll open a new tab and do some real stuff. All right, so now I have this Vault server running, and it runs in a client-server architecture. And the easiest way to interact with that Vault server is using the Vault CLI. The Vault CLI will handle things like authentication for us. But under the hood, every command I run here today could be replaced with like curl or your own language. So if you work in a language that can make an HTTP or HTTPS API call, you can interact with Vault at the application layer. So I'm going to log in as the root user. This is not a best practice, but this is a live demo. I'm now the root user. It's kind of like sudo or root in Linux. I have full all permissions in the system. Usually when you have this user, you delete it after you're done with it, or you restrict it to a very small subset of users. So let me create a couple users in Vault. There's a few ways in which users authenticate to Vault. So you can think of Vault in some sense as an identity broker. You can log into Vault with things like a username and password, which is what we'll do here. You can authenticate with things like GitHub or LDAP or Active Directory credentials. That's a human, though. But Vault tries to be a single source of secrets for both humans and machines. So if I'm a machine, I don't log in with Active Directory. That doesn't make sense. Instead, I might log in with something like a TLS certificate. Or I might log in with trusted metadata from my cloud provider. I might trust Google or Amazon or Azure, and I say, if this instance belongs to you in this particular instance group, then give it authentication. So Vault supports both machine and human-based authentication mechanisms. All right, so we've created a couple of users. We'll come back to this in a minute. Let's use Vault's kind of first thing, which is a static key value store. So one of the things that Vault can do is it can act as a static key value store. What's the Wi-Fi password? DevOps 2018? It doesn't matter. It's a demo. So I put some data into this key value store. You can think of this as like encrypted Redis or encrypted memcached. I put data in. It's encrypted in transit with TLS. It's encrypted at rest with 256 CBC encryption. When I want the data back out, I ask for it back, and I get the secret back out. You can see that this is versioned. For those in the back there, the Wi-Fi password is DevOps 2018. I can update this value, so I can say secret/foo Wi-Fi is actually not DevOps 2018. What did I do? Vault kv put. And now you can see that this is version 2. So it's automatically versioned. You keep a versioned history of all the changes. We can get this value. We see it's not DevOps 2018. And then we can actually restore the old value if we actually messed up. And even though this is version 3, it's reverted back to the value of version 1. So you can think of this as encrypted Redis, encrypted memcached. You put data in, Vault stores it. You want the data back, Vault authenticates you and gives it back. We can also, as you would expect, delete things, etc. How many people feel more secure? Yeah, so I always like to talk about this. Vault has been audited 9 times by the NCC Group, which is an independent auditing firm. It continues to pass with flying colors. So like, this is secure. Independent security researchers have proven that. Yet it doesn't feel secure. And the reason for that is because as an industry, as a technology industry, we've been conditioned to believe that security has to be hard. If you don't like base64 encode it and then like duct tape it to the back of your Tesla and drive it down the road, then it can't possibly be secure. We have to go through all these steps. It has to feel hard. And that's just not the case. It's possible to do security in a way that is easy and pragmatic. And Vault, hopefully, as I'll show you, makes that possible. So this key value backend is really cool. We can put data in, Vault stores it, we can get it back. But what if I have a lot of data? Like, Vault is not a replacement for a database. So you should not use the key value store for encrypting things that should belong in a database. Things like credit card numbers or passport numbers or anything that you need to decrypt later and get the plain text value back out. So let's say for some reason you have to process your own payments. You can't use a credit card processor like Stripe or an API gateway for that. You need to store credit card numbers. You can't just salt them and hash them because you need the plain text values back so that you can process that credit card. So you need to encrypt them. And if you have 1 million customers, that's 1 million rows in your database, 1 million credit cards that you have to manage. This is where Vault's transit backend comes in. Unlike the key value store, the transit backend encrypts the data and then gives it back to you. So it's very similar to like a KMS provider from a cloud provider. You give Vault some plain text data, Vault encrypts it with a key that it manages, and it gives you back the ciphertext or the encrypted data. It's then your responsibility to store that. You put that in the database, whatever. When you want the plain text back, you go to Vault and you say, hey, I'd like the plain text. Here's my ciphertext. Vault decrypts it, assuming you're authenticated and authorized to do so, and then you get the plain text back. So let's go ahead and enable the transit backend. I can type. So now I've enabled the transit backend, and I'm going to create a key. So secret or transit keys. And I'm going to name the key my app. So now I have a key named my app. Under the hood, my app is like a symlink or a pointer to a bunch of bytes that represent an encryption key. So when I ask Vault to encrypt some data using the my app key, it's actually using the underlying encryption key. So let's try that. Transit encrypt my app, and I'm going to give it some plain text. What plain text should we give it? DevOps. Okay. And it says legal base64 data input character input byte 4. What does this mean? Well, there's no requirement that the data I'm giving Vault is actually ASCII representable text. I could be giving it a PDF or a Microsoft Word document, for example. So the Vault API actually requires that we base64 encode this. But that's easy. So now we get back the ciphertext. And this ciphertext is what I put in my database. So I would, copy this, put it in my database. Okay, 6 months later, we need to get this value back for whatever reason. So I ask the transit backend to decrypt this value. And we don't have to base64 encode the ciphertext. It's already URL safe. And we get back zigavigit 2-bigit 29 waka equals. But if we copy this to our clipboard and decode it, we'll get DevOps. Right? This backend also supports rotation and upgrading of the keys. So for whatever reason, we need to rotate the underlying encryption key. We can do that. I've now rotated the key. Remember that this here was our first value. You note the v1 there. If we come back here and re-encrypt that same value, note that it's now a v2. That means it's using a different encryption key. And we can actually upgrade those encryption keys over time. So that allows you to do things like rotate your keys every 30 days. That ensures that your data is always being encrypted with a new key, but you can always decrypt old versions with old keys. So this is really just kind of scratching the surface of Vault. We can put static key value data in. We can put static data in and get kind of this encrypted transit back. That's our responsibility. But earlier I talked about provenance, which is this one-to-one mapping between a credential and its user or machine. How do I make a database credential without involving a human? Right? Like at some point a human has to like SSH into the Postgres server and like run commands, right? Like how could I possibly generate a database user without a human seeing that credential? Well, this is where Vault comes in. So I'm going to start a Postgres server using Docker. And then I'm going to enable this database secrets engine. What the database secrets engine does is it configures Vault to be a very privileged user in this example, Postgres, but it supports MySQL and MariaDB and Oracle and even HANA. And give Vault some initial set of credentials. Vault then rotates those credentials so only it knows them. Then Vault programmatically generates users on demand via the API. So let's take a look at what this setup looks like. Configure database. So this is a script because I suck at typing, and this would be a 50-minute talk. The first thing we do is we enable the Postgres interface in Vault. So what this does is this is effectively telling Vault, hey, Postgres is here, and here's your kind of initial username and password. Vault can rotate those later for us. I'm using a local Postgres Docker container, so that's why it's localhost. Then here, the second statement here is really the key to this entire configuration. We're creating a role named read-only, and we give Vault the creation statements. So we actually give Vault the SQL that we want it to execute on our behalf. So instead of a human connecting the Postgres server, running all these commands, Vault is doing that for us. The DBAs gave us this stuff, and we parameterized it. So this curly brace name and curly brace password and curly brace expiration, these things get filled in by Vault each time Vault executes this command. So no longer should a human connect to Postgres to create these credentials. Vault will do it for us. We're granting select on all the tables, which is why this is a read-only user. Makes sense, right? The reason you have to give Vault the SQL is Vault has no idea what permissions you want to grant, and it is not SQL compliant. So you give it the SQL you want it to run. This could be a stored procedure, some type of function, and you just put in the curly braces for the things you want Vault to complete. You'll also notice this default TTL and max TTL, which I'll talk about more in a second. But let's go ahead and run this now. Oops. So I've created that role. And now what I'm going to do is I'm going to read a credential. I can spell. So that was really fast, but let me explain what just happened. Vault established a connection to my locally running Postgres Docker container. It dynamically generated that username and password that you see there, at the very bottom. It injected those into the SQL creation statement that you saw in the script earlier and executed that against Postgres and created a user. It then returned the username and password to me. An important thing to note is that Vault did not store that password. So even if an attacker compromises Vault, they would only have the username, because that's the only thing that gets stored, because that's the only thing Vault actually needs to manage this particular user. The password is in transit. It's just given to you, but it's not stored. Notice that there's this least duration thing. In Vault, all credentials have a lifetime. So unlike the traditional use case of I create a credential and it lives forever, Vault enforces what we call a lease or a TTL. In this example, this credential is valid for 15 minutes. At the end of 15 minutes, this credential will expire. When it expires, it'll be removed from Postgres automatically. Vault handles that for you. You can optionally allow this credential to live for up to 24 hours, because that's what I configured it. So you can tell Vault, hey, I'm still using this credential. This is conceptually similar to IP addresses. Right? When my laptop gets an IP address from the DHCP server, it comes with a lease, 8 hours. At the end of 8 hours, it's my laptop's responsibility to go back to the DHCP server and say, hey, I'm still 10.whatever.whatever.whatever. At that point, the DHCP server might say, great, you can have it for another 8 hours. Or the DHCP server might say, no, here's another IP address. But if I close my laptop and go on vacation and come back, the DHCP server might say, no, I've already given your IP address to someone else. Your TTL is expired. Here's your new IP address. My computer handles that for me transparently. Vault does the same thing, but for credentials. They expire, they can be renewed, and they can be force expired or rotated early. So let me log in as a new user now. So earlier we created some users, and I'm going to log in as Chris. And Chris's password was password because he's not very secure. And I'm going to read a credential again. Oops. So now we have 3 credentials in Postgres. The original Postgres root user, the one that I created as the Vault root user, and the one that I just created as Chris. So let's see what that looks like. Sure enough, I have 3 users. I'm going to just back up here for a second so you can see. So I have the Postgres user, I have the token, the one that I created as the root user, and the one that I created just now as Chris. And you can see that they both have this password valid until clause, which means the credential will automatically expire at that time. So let's simulate a real, air quotes, production-like thing, where I'm just going to create a whole bunch of credentials. And the goal here is to simulate like a production environment where there's a bunch of different applications that have all requested different things. So just to prove that I created a bunch of credentials, there's a whole bunch of things in here. There's a whole bunch of things in here. But like, what if an application is compromised? Or what if there's a data breach? Or in this example, what happens if both Chris and Devin are fired? They did something, their manager didn't like it. We should probably not let their credentials live on. So what we can do is we can actually revoke all of Chris's credentials, and we can revoke all of Devin's credentials. Oops. All of Devin's credentials. And what this does is, under the hood, it automatically iterates over everything that they've done in the system and deletes them. So we still have a couple of users in here, but we don't have the ones from Chris and Devin. But what happens if we have a much larger data breach, like an Ashley Madison style data breach, where like it is better for us to take downtime than it is to continue allowing people to access our data? Well, we can actually just revoke, sorry, make this bigger. We can just revoke all of the database credentials. Oops, that's a deprecated command. It's really embarrassing because I deprecated that command. And now, when we run du, we have one Postgres user. So it actually revoked all of them. And that's automated, right? This is an API under the hood. So anything I just did here could be automated by a script or a button in a GUI. Let me quit Postgres here. So Vault really tries to be this single source of secrets. And when you think about secrets management, you think like usernames, passwords, APIs, certificates, those types of things. And it does all of that. But how many people here work on a website that offers multi-factor authentication for users, user-facing multi-factor authentication? How many people have ever written or read the TOTP white paper? Yeah, probably not, right? I have, and I wish I didn't, because it's really complicated. But this is where I think Vault really pushes the boundaries of what we think about as secrets management. It can act as both a secrets, a TOTP provider and a TOTP authenticator. So instead of you writing the algorithm or using some third-party library, you get TOTP as a service. Similar to something you might buy from someone like Duo or Authy, but you can implement this internally with Vault. So I'm going to go ahead and create a TOTP code for myself. I'm going to ask Vault to generate it. I'm going to say the issuer is DevOps, and the account name is my email. Please don't spam me. Cool. So we get two things back. We get this barcode, which is a base64 encoded PNG, and we get back the URL. So I'm going to echo that PNG, and I'm going to base64 decode it, and I'm going to put it in a PNG file, and then I'm going to open that PNG file. Oh, look. And then I have this cool app called 1Password, which I'm not endorsing. It just makes my demo really cool. I can actually scan this QR code, which is the same thing your user would do with an app like Google Authenticator or some other authentication app. We drag this, oh, darn it. We drag this over here. It turns green. We get a TOTP code. Hopefully it doesn't expire before I type it in. Oh no, what did I create my code as? Oh, I called it TOTP. This is okay, and I'm still valid, right? So this is TOTP as a service. All right, I have 6 minutes. The last thing I want to show you is that it's extensible. there's a huge surface area for Vault. It covers a ton of different things. But if for some reason you have some proprietary software that you need to integrate with, you can actually write a plugin. It has a first-class plugin system. So I wrote a plugin that's really popular, which generates passwords and passphrases. I have mounted it already. So I can ask Vault to generate me a password that is 64 characters long. 64 characters long. And it uses Go's crypto random library, and it gives me a password. So if you're running a service where you provide your users like some type of auth token or some type of temporary password to log in, each time you run this, you'll get a different password. You can vary the length of the password. You can control whether there are symbols and uppercase and lowercase letters and numbers. It also supports the diceware algorithm. So instead of a password, we can generate a passphrase. This is like the famous horse staple battery XKCD thing. This will generate kind of 4 memorable English words that you can use as a password instead. So I'll go back to this thing. So that's all I have for you here today. I know it was a lot. I'll be around to answer questions. I can take them now or in the Dev Center. If you have questions that you don't feel comfortable asking me, you can always tweet at me. My direct messages are open on Twitter, but I'll be around the rest of today. Thank you very much.
Questions, guys? Arms up.
Over there.
Mm-hmm.
And I was cheating. I don't memorize those commands. They're on my phone. So.
Hello, and thank you for your keynote. Does Vault provides any integration with Kubernetes? And I know that it provides you a way to store your secrets, but does Vault does anything beyond that in cloud environment?
Sure. So the question is, basically, does Vault integrate with a tool like Kubernetes? It does. You can go to my GitHub, Seth Vargo /vault-on-GKE, which is the Google Kubernetes engine. That'll give you a Vault cluster that's running on Kubernetes. There's 2 answers to that question. Can Vault run on Kubernetes? Which is yes, it's very easy. I have a set of Terraform configurations that'll do it for you, and Kelsey Hightower did the hard way for running Vault on Kubernetes. The second question is, I have pods and services. How do they connect to Vault to get credentials? That is also a solved problem. There is a Kubernetes authentication method. So you can give your pod's service account to Vault. Vault will verify that using Kubernetes Token Reviewer API, and then issue a Vault token based on the namespace and the bound service account to that pod. From there, you can issue standard API calls. I also have a pod called the Vault Kubernetes Authenticator that does that whole flow for you and gives you a Vault token in an in-memory volume mount. And then you can use tools like console template or env console to get the secrets into the pod at runtime. I said all of that very fast. If you just Google search Seth Vargo Vault Kubernetes, there is a talk on YouTube that I gave at Google Cloud Next in July that is a full 50-minute talk that walks through all of that much slower. Or you can find me at the Dev Center, and I'll give you a bunch of links.
Thank you. One more question.
In the back, I think?
Yeah. I'm coming.
Since we are talking about Kubernetes, am I right that there is a project on GitHub with Vault on Kubernetes setup, and it is yours?
Sorry, I can't really hear. Can you talk a little louder?
There is a project on GitHub with Vault setup on Kubernetes. Am I right that this is your project because it differs from HashiCorp's default install?
There's a project on GitHub that runs Vault on Kubernetes.
Yeah. It's battle hardened Kubernetes setup. I thought that was your project.
I don't know what the differences are.
Okay. Are you using like default Helm installation that HashiCorp provides, or does your production Vault setup differ greatly from it? That's my question.
Everything in my setup has been approved by both the Google Kubernetes security team and the Vault team at HashiCorp. So I'm not sure what other repo you're talking about, but all the stuff that I've done is production grade. It's in production at a number of financial institutions.
Okay, Jill, so I may take a look at your setup and I can be sure that it's like really good.
Yes.
Yeah, okay, thanks.
Well,
I think we're out of time.
I guess we have time for only one question. Real
I saw
quick.
this one first. I saw
Okay.
this one. Oh, okay.
Who was first?
Sorry.
Who was first? Who was first? Let's be fair.
So did I get it right? So anyway, you Vault relies on hardware encryption anyway, as far as it keeps secrets, private passwords to decrypt the data, right? So it relies on hard drive encryption anyway.
No, so Vault itself manages its own keyring. I can go into detail about the Shamir secret sharing algorithm and how Vault encrypts data at rest. Even if you're using like the file system, Vault still encrypts the data before it writes it to the file system using an in-memory keyring.
Yeah, but it needs the key to decrypt it anyway. Where the key is kept?
So this requires a whiteboard. There's this algorithm called Shamir secret sharing algorithm, which allows you to take a string or a series of bytes and split it up into a subset such that, let's use concrete numbers. I have a string A, B, C, D, E, F to Z. I can split that up into 5 pieces such that any 3 of those 5 pieces can come together to form the original string. It uses intersections along polynomial graphs. There's a Wikipedia article on it. Anyway, it's very common in secrets management. What it allows you to do is Vault generates its encryption key. It then generates this thing called a master key, which is immediately split apart into this configurable number of shares. So you give 3 to 5 to 10 people in your company a piece of that share. And then a subset of those people, say 7 of 10, come together to unseal the vault or to bring a vault online. That reconstructs the master key, which decrypts the encryption key, which then decrypts the rest of the data in Vault. This is why I said I need a whiteboard.